So here we've got a question. We want to find an upper estimate for this integral here, e to the z over z with regards to z over the contour c. Now c is a closed contour and it's where the absolute value of z equals 2 and the imaginary part of z is greater than or equal to 0. So before we get on to actually answering the question and use the estimation theorem, let's just have a look at this contour, see what we're dealing with. So a little diagram here, real and imaginary, and I recommend you do this with all your complex analysis. Real part of z is 2, so if I put positive 2 there and negative 2 there, so this would give us a unit circle, but here we've got the imaginary part of it is always greater than or equal to 0, so basically it's the upper half. So we've got some kind of arc there, so it goes in the anti-clockwise direction, so that's what we've got for C. Now we're going to use the estimation theorem to find an answer to this question. So what we're looking for is two constants. So the estimation theorem tells us f of z dz, that has got to be less than or equal to two constants ml, sometimes called the ml inequality. Now L is the length of the contour, so that's usually the easiest part to deal with. So I recommend you take care of that bit first. So length of the contour, so I'll put C in this case. Sometimes people use gamma, it doesn't matter. As long as we're defining this correctly, it's okay. So the length of C. So before I go on to M, let's just find out what our L is. Now L is the radius, circle of radius 2. We want the circumference, and the circumference of this will be 2 pi r over 2, which is just pi r. And as the radius is 2, it's just 2 pi. So the length of that is 2 pi. So that's our L constant taken care of in double quick time. So that's fine. Now we want to find M. Now what we want to do for that is just take out our integrand and f of z. And let's take the absolute value of that, and that to be less than or equal to some value M. So in this case, our f of z is e to the z over z. So let's define our f of z. Now to get some kind of maximum of this, as it's a quotient, we need to find a maximum of the numerator and a minimum of the denominator. So that's what we want to do there. So now what we're looking for is e to the z over z. So let's maximize that. So e to the z, let's break this apart. That is the same as the modulus of e to the z over the modulus of z, so that's fine. Now the exponential identity in complex analysis of the modulus of e to the z, that's just the same as e to the real z. So now I've got e to the real, let's just write real, write that properly, e to the real z over the modulus of z. Now the modulus of z is defined in the actual contour, which is 2. So that's over 2. Okay, now what's the real part of z? Well, the real part of z, well, that's just 2. So we've now got e to the 2 over 2, and absolute value of that is just the same as this, because this is always going to be positive, e squared over 2. So now with this we can just define our ml. So ml, that will equal e squared over 2 times 2 pi. So we just need to make sure before we finish with our answer that this is a continuous function. Now e to the z over z, now if z equals 0, this would not be a continuous, there'd be a singularity there. But as we're dealing with a unit circle circumference, the actual z equals 0 is never on our contour. So we're quite happy that this is continuous. So now we can define our ml, just multiply through, and that would equal pi e squared. So that would be our maximum value. Now with the ml inequality using the estimation theorem, this will not always be the only answer. Sometimes you can get different answers. So we're looking for an answer with not too much complicated algebra and a reasonable estimate that's not ridiculously large. So this looks to me like pi e squared is going to be a reasonable answer. So in this case here, our answer is pi e squared. and I'll be happy to define that as our answer to this question. Okay,